In this module, we're going to lay down a working definition for what exactly we mean by the term engineered system or technology, as we'll be using the two terms interchangeably. What we want to try and do here is get a grasp on some of the fundamental characteristics that remain invariant whether we're talking about a very simple technology, like a shovel, or a very complex one, like an airport. Many factors will change with the scale and complexity of the system, but the fundamental features to technology will remain continuous, and this will give us something to ground our analysis in. Because in this world of globalization, information technology, and large infrastructure systems, things can get very abstract and complex very quickly, and we don't want to lose sight of the fundamentals to what we're dealing with. So let's start from the beginning then, and the beginning is us, human beings. Because unlike other systems in the natural environment, such as stars, stones, or plants, that are governed and shaped by natural processes, technology is not. It is almost exclusively created by human beings, for human beings, and thus it is governed and defined by a logic that reflects the condition that we're under. So what is this condition? This condition consists of the fact that we are biological creatures in a physical environment. Like all biological creatures, we require a constant input of energy and resources. We are persistently and actively engaged in trying to maintain and develop our access to the resources required for our self-preservation and development. Like all creatures, we maintain and alter our environment in order to achieve what is called homeostasis. That is to say, an environmental condition that is optimal for our self-preservation and well-being. Unlike other creatures though, we have developed the capacity of advanced cognitive processing, which has made us somewhat distinct from other creatures, and is ultimately the foundation that has enabled civilization. With this advanced cognitive capacity, we are able to create complex models of our environment, understand a wide array of cause and effect interactions. We can conceive of desired optimal future states, use logic to try and achieve these through a sequence of strategic actions, and this is the very abstract foundations to technology and engineering. The word engineering comes from the word meaning clever solution. In its essence, it is about developing systematic methods for solving some constraint. Technology is then the embodiment of this systematic solution within a physical form that can then perform the set of stages required to resolve the constraints whenever needed. The economist W. Brian Arthur defines technology in a similar very broad way, as a means to fulfilling a human purpose, but we'll try to give this a bit more definition by creating a simple systems model that should aid us in our reasoning. In this model, we have a current state A and a future desired state B. This could be anything from being on one side of a river, state A, and wanting to get to the other side, state B, or being cold and wanting to get warm, and so on. We then have some kind of environmental constraints between state A and B. These environmental constraints generate the problem space that we need to resolve in order to get to state B. Engineering, then, is the development of an algorithmic process to solve this problem space. That is to say, a set of steps that need to be performed in order to get to our desired state. Technology is the actual system that performs this process, taking us from A to B. In this way, we can then think about technologies as systems, in that they have some input of resources, and they perform a function on these inputs in order to produce some desired output. Although technologies are different from natural systems, as we've already noted, we can only properly give them context by understanding them as also extensions of natural processes. Technologies are both a very organic part of human beings and an extension of us. Almost all technologies can be traced back to some initial process that was performed by our unaided natural physiology. Whether we're talking about transportation performed originally by walking, or telecommunications performed originally by our vocal system. Through endless iteration of these natural processes and innovation, we have rationalized these processes and embodied them in external automated systems that can typically perform the process more efficiently and effectively. By automation, we mean that through having rationalized this process, we no longer have to look for a solution to it each time. The technology is the solution, we just have to operate it. The word automatic means acting by itself. In other words, the technology has automated part of the process. I don't need to think about how I'm going to get to work each day. I simply get in my car and drive. I don't even need to know how it actually converts the input to the system, that is liquid fuel, into the functional output, that is personal mobility. And I don't need to think about it because the technology was designed specifically to automate this process. All systems operate at some degree of efficiency, and efficiency is a central concept in engineering. The second law of thermodynamics tells us that in this processing of energy and resources, there will always be an increase in entropy. That is to say, when we run this technology system, it will produce some waste product that either remains in the system, degrading its functionality over time, or gets exported to its environment. When I operate my car, only about 25 to 30% of the energy released by the fuel is used to move the vehicle. The vast majority is rejected as heat without being turned into useful work, and this entropy must be exported from the system or else it will damage its functioning. This entropy, of course, does not just disappear. The heat, along with other forms of waste, such as noise and gas emissions, go into the system's environment. From this, we can define the system's efficiency and begin to reason about its sustainability. Sustainability is another very abstract concept, but in its essence, it describes the relationship between a system and its environment. It is essentially a function of, on the one hand, the volume of resources the system requires, coupled with the environment's stock of resources accessible to the system, and on the other hand, the amount of entropy the system produces, combined with its environment's capacity to absorb that entropy without degrading its capacity to continue providing the system with a future supply of resources. In trying to overcome some environmental constraint, we also manipulate the environment. We alter it according to our set of instructions. An artificial system, then, is one that is designed according to some set of principles that do not integrate with the natural processes and thus work to disintegrate the natural environment. This might also be called hacking, the re-engineering of a subsystem within a larger integrated system in order to optimize it according to a set of principles that do not integrate with the overall pattern of organization, and thus work to disintegrate the macro system and reduce its sustainability. Optimizing a computer's processing unit for speed, what is called overclocking, is another example of hacking. We are optimizing a subcomponent and thus breaking or disintegrating the computer's overall design pattern, which will ultimately work to reduce its long-term functionality and sustainability. When we talk about sustainability and a technical system within its environment, we're no longer just dealing with the quantitative technical efficiency of the system. We have to also ask the qualitative question of why we use the technology in the first place. When we run a system, it produces some output. If this output is immediately consumed without becoming the input to a new process, then we can refer to this as dissipation, meaning that the energy is dispersed or scattered, thus increasing the entropy and decreasing its capacity to do work. The resource has been used up and is no longer available for work, at least not at the same level of functionality as before. If I use my iPhone to play computer games, the output to this process can't be used to enable another function. The resources inputted to enable the operation of that technology have been dissipated. Dissipative processes generate entropy and are typically time irreversible. We can't take the output and go back to feed it into the input again because it has been degraded during the operation. Inversely, the output to this system might be used to fuel another. For example, the processing of crude petroleum within a refinery is required in order to produce the input for a vehicle of transportation. This is an example of an anabolic process. That is, one that requires an input of energy in order to refine or synthesize basic resources into resources of a higher quality. The assembly of parts on a production line into a finished product is another example. It requires work to be done, that is to say, the system performing a function in order to produce some throughput of a higher value. The conversion of coal into electricity is another example, as electricity is a much higher quality energy than coal. With functionality and throughput, we get what is called emergence. When we're supported by a system of technologies that are working effectively, they enable us to function at a new level of organization. Technology offers the possibility for us to be more productive and live a better quality of life. Infrastructure systems are good examples of this. Unlike consumer goods, the throughput to infrastructure systems like transportation and electrical power networks enable other technologies to function more efficiently. In this way, we get emergence as we move up the different levels to our technological substrate, and thus the infrastructure systems that form the base of this can have a powerful leveraging effect, where when you invest $1 in infrastructure, you can get $3 worth of overall economic value back. New levels of organization to our systems of technology emerge as we go from basic tools to industrial machines to information technology. When these systems work properly and are abstracted away through encapsulation, we can sit on a high-speed train, sipping our cup of coffee and surfing the web, completely oblivious to the many layers of technology that are required to enable this. When we get functionality, throughput, and emergence of a multi-leveled system, with everything being properly abstracted away, we can get the smoothly running infrastructure systems like that of Hong Kong and Switzerland. Consumer goods like iPhones and sports cars may be the celebrities of technology, but they're enabled by a multi-tiered infrastructure that makes our globalized world go round. To summarize then, no matter how complex, sophisticated, or large the technology we're talking about, whether we're trying to peel a potato, build a website, or move millions of people around a city every day, we're always dealing with the same basic features to technology that we've been discussing in this module. That is to say, that we wish to get from one state to another more desirable state, and there will be some environmental constraints that we need to overcome in order to achieve this. There will be a large possibility space for how we do this, but through engineering, we rationalize the process to develop an optimal automated solution, what we call technology. This technology is a system that performs a function. It performs this function only ever to a limited extent and thus generates entropy during its operation. Its degree of efficiency and the environmental conditions define its degree of sustainability. When many technologies work together as an integrated system, we get emergence as new levels of organization emerge to create multi-level platform technologies, and this is the technical substrate that our societies depend upon.